This is a brief introduction to 2.6, rational functions and asymptotes. So they give us, we're going to be working with this form here, f of x equals n, standing for numerator of x, over d of x, denominator of x. Now the domain for this function is all reals except x that make d of x equals 0. And they start off with example 1, f of x equals 1 over x. And we want to examine the table and the graph and look at the example, and then so we do that here. Here's the table. You can see what's happening. As x approaches 0 from the negative side, y is approaching negative infinity. So let's look at the graph. As x approaches 0 from the negative side, y is approaching negative infinity. So you approach 0 on the x-axis, and y is plummeting downwards. As you approach 0 from the positive side, y is approaching positive infinity. Okay? So we got asymptotes there. Y will never reach positive infinity, and x will never reach 0. So there's our, we have a horizontal asymptote at y equals 0, right here. As x goes on to infinity, it approaches 0 but never reaches it. I'm sorry, as x goes on to infinity, y approaches 0 but never reaches it. So we have a horizontal asymptote at y equals 0. Then we have a vertical asymptote at x equals 0. Now, exercise 5. F of x equals 1 over x minus 1. Now we're just going to use this notation here to keep ourselves familiar with it. So 1 over x minus 1 equals f of x. The domain is going to be is all reals. X is all reals such that x is not equal to 1. Okay, and then we're going to make a little table of values to see what's going on. And as x, what you do is, if you're going to make a table of values about a rational function, make some of the values to the left of the asymptote and some to the right. But in exercise 5, let's take a look at exercise 5 here. Alright, here is you're supposed to fill out these tables. Okay, so they're filled out here, and so when x is 0.5, f of x is negative 2, and x is 0.9. So you can see what's happening as x approaches 1, y approaches negative infinity. In this table here, approaches 1 from the left. Okay, or I should say from the right. Okay, so here's x at 0.5 right here, and then 0.9, 0.99, and 0.999. Okay, and y is approaching negative infinity. Okay, and then in the next table we have x approaching negative infinity and y approaching 0. So x approaches negative infinity, so x gets bigger and bigger in the negative direction, y approaches 0 from the negative direction. Negative 5, negative 10, negative 100, negative 1,000, and so on. Okay. And here's x approaching y from from the right, going to the left, 1.5, 1.1, 1.01, and now y is approaching positive infinity. And here is x approaching positive infinity, and y is approaching 0. So 5, 10, 15, 5, 10, 100, 1000, and f of x gets closer and closer to 0. Alright, next section, vertical and horizontal asymptotes. Okay, and then here's the notation. This is very important. You can read this as f decreases without bound as x approaches 0 from the left, or as y, as f of x approaches negative infinity, x approaches 0. As f of x approaches infinity, x approaches 0 from the positive side. And so we have some definitions of asymptotes. You already know these. Okay, the line x of equals a is a vertical asymptote of the graph of f when f of x approaches positive infinity or f of x approaches negative infinity, as x approaches a either from the right or the left, and so on. Okay, now these functions are interesting to look at. We got 2x plus 1 over x plus 1. And we want to think about what's happening here. We got 2x over x, and that makes a horizontal asymptote of y equals 2. And we'll talk about the rules for that in a minute. And you can see that the domain for this function is going to be all reals except x equals negative 1, and so we have a vertical asymptote at x equals negative 1. The second function, 4 over x squared plus 1, x squared plus 1 has no real zeros. So it's it does not have to the domain is all reals. And there's no so as x increases without bound, then as x approaches positive infinity, then y is going to approach 0. So you have a horizontal asymptote at y equals 0. And then the last function has two vertical asymptotes, x minus or 1, I should say, at 1. Okay, and the function approaches from either side. Graph approaches from either side. Now let's look at the box on page 144. Now this is really important, the stuff that's here. You have the definition of the polynomial for the numerator and denominator. However, the only term we have to consider in making the important decisions with these rational functions is the first term. A sub n times x sub n over b sub m times x to the m. So, number one, the graph of f has vertical asymptotes at the zeros of d of x. Okay, we know that. 2, the graph of f has at least one horizontal asymptote determined by comparing the degrees of the numerator and denominator. Now, if n, the exponent of the numerator, is less than m, the exponent of the denominator, then the graph of f has the line y equals 0 as a horizontal asymptote, always. So, if you have x to the squared over x cubed, doesn't matter what the coefficients are, x to the 50th over x to the 51st, you're always going to have a horizontal asymptote of y equals 0. B, if the exponents of the leading terms are equal, then you will have a horizontal asymptote that is the ratio of the coefficients of the numerator and denominator. So a sub n over b sub m, always always. That's if the exponents of the leading terms of the numerator and denominator are equal. If n is greater than m, so you have x cubed over x something times x cubed over something times x squared, then you will not have a horizontal asymptote. Now we'll get to those later. You're going to have what's called a slant asymptote. We didn't do those in Algebra 2, but we will do them this year. So, now you may want to take, there's kind of an interesting thing here. According to our rule, the polynomial in the what's wrong box should have a horizontal asymptote at y equals 2, since you have 2x cubed over x cubed as the ratio of the leading terms. And that the horizontal asymptote settles out to be 2, but it doesn't start out that way. And so if you graph it with a window of -10 and 10, you're not going to see 2 as the horizontal asymptote. And that's because, well, you can play with it in the calculator. I encourage you to play with it and see if you can figure out what's going on. All right. So example 2, let's look at this. Find vertical and horizontal asymptotes. Okay, 3x squared plus 1 has no vertical asymptotes because it has no real zeros. Now, but the degree of the leading term, okay, so let's look at that. Okay, a sub n times x to the n over b sub m times x to the m. M is greater than n, so there's a vertical asymptote, there's a horizontal asymptote at y equals 0. Okay, now b, the denominator, x squared minus 1, has plus minus 1 is 0, so plus minus 1 are vertical asymptotes. X equals 1, x equals -1. Now, let's use the model a sub n times x to the n over b sub m times x to the m. N equals m, so the horizontal asymptote is y equals a sub n over b sub m. In other words, the ratio of the coefficients. Y equals 2. So let's do exercise 17, 1 over x squared. X squared. Okay, well, we have a vertical asymptote at x equals 0, obviously. And the degree of the numerator is 0, and the degree of the denominator is 2. So we have a horizontal asymptote at y equals 0. All right, now let's move on. Finding asymptotes and holes. Now we have to sort of refine our sense of asymptotes with vertical asymptotes, and namely, here's what's going on. You've got a polynomial in the numerator, a trinomial in the numerator, a trinomial in the denominator, degree 2. You can factor them. So let's factor the numerator and denominator. Meanwhile, let's recognize that m equals n, so the degrees of the numerators and denominators are the same. And a sub m equals b sub n. In other words, the coefficients are the same. So the horizontal asymptote, there would be in the ratio of 1 over 1. So y equals 1. Now let's factor the denominator and numerator. This will help us find the zeros for the denominator. We got x plus 2 times x minus 1 over x minus 1 times x plus 2. Note that the x plus 2's cancel. So x minus 2, the root of the factor x plus 2, is not a vertical asymptote, but is instead what's called a hole. So the graph is continuous up until negative 2, but it doesn't, negative 2 is not an asymptote. The graph will go right up to negative 2, and then there'll be a hole, and it continues right after it. And y does not approach infinity on either side of negative 2. Now, x equals 3, so negative 2 is not an asymptote, but a hole. But x equals 3 is a vertical asymptote. And then let's just note, for the sake of everything, that f of 1 is 0. So it doesn't ask you to do this, but I put in the plot the asymptotes. We're going to graph one of these things by hand. First thing is, put in the vertical and horizontal asymptotes with dotted lines, preferably. And you want to put in, now I also graphed the hole, okay, which is at negative 2 and 3/5. So that's this, here's the hole at negative 2 comma 3/5. And then to graph the rest of your rational function, if you plot a couple of points to the right and a couple of points to the left of the vertical asymptotes. If you got more than one, then you're going to have to do that with the other asymptote as well. And that will give you both parts of the hyperbola that makes up this thing. Okay, so I chose, so I have a vertical asymptote at 3, so I chose 4 and 5, and then I took 2 and 1. And that's going to give me all the points I need, including this the whole, to effectively label the graphs, and remembering that I'm approaching these asymptotes but not reaching them or crossing them. Okay, now we go on to exercise 23. X squared minus 25 over x squared plus 5x. Now I like using this notation just so I get everything into my head as far as these rules go. So let's use the rules. M equals n, so a sub m equals b sub n, and a sub n. So the horizontal asymptote is y equals 1. So let's factor the numerator and denominator. We got x minus 5 times x plus 5 over x times x plus 5. The x plus 5's cancel, so negative 5 is a 0. Negative 5 is a 0. Well, it's not a 0 exactly. It's a whole. Okay, x equals 0 is a vertical asymptote. So f of 5, negative 5 equals 0, and f of 5 equals 0. So we end up graphing x minus 5 over x. So just to recap, x equals 0 is a vertical asymptote, f of negative 5 is a whole, and f of 5 equals 0. You can use that to graph it, but the problem doesn't actually ask you to graph it. Okay, now example 4, finding a domain and asymptotes. Pretty straightforward. So again, we're just going to factor. First we'll look at horizontal asymptotes just to get that out of the way. And we're going to see again the degrees are the same of the leading terms. So the horizontal asymptote is going to be negative 3 over negative 2, or negative 3 over 2 equals y. So let's factor the denominator, and we end up, we take negative 2x cubed plus 16 equals 0. We got x cubed equals 8x equals 2. So a vertical asymptote at x equals 2. Now notice I found out what value of x is going to make the denominator equal to 0. Okay? So the domain is all reals. X is not equal to 2. Let's do exercise 25. 3x squared plus x minus 5 over x squared plus 1. Now the domain is all reals. X squared plus 1 has no real solutions. Therefore the function has no holes, since x squared plus 1 does not factor and does not divide into the numerator. The horizontal asymptote is going to be a over b, which is 3. Okay. Now there are some real zeros, and you can put this into your calculator and see what the graph looks like to verify your results. Now, there's one interesting thing about this. Let's take a look at it. Let's take a look at this problem for 25. Get the calculator up here and find the state for 25. Okay, now in order here's the graph, what it looks like. Now let's look at the table. Now when you weigh negative, you can see as x approaches negative infinity, let's get more and more negative. Okay, you can see it's approaching 3, and that's good. Okay, that's what you would expect. Let's go back the other way. Let's go in the positive direction. And this graph is going to do something that you don't expect. It is going to get bigger than 3. So it gets bigger than 3, but I thought, these functions were supposed to cross asymptotes. Well, that's when they're simpler. That's when they're in the form of y equals a over x minus b or whatever. So it crossed 3, but as x gets bigger, now it's coming back and approaching it. So 3 is the asymptote for this function. But on the positive side, the graph will cross 3 and then gradually come back down towards it. Let me stop this thing or whatever a second. Okay. All right, let's go back to here. The final example, we're going to a word problem. So they want to remove pollution, and there's a couple of problems that we have with this. And the cost, this is called cost benefit. So here is the formula for it. To remove each percent costs $80,000. The units is dollars. Okay, over 100 minus p. So, and the domain, obviously is going to be from 0 to 100, where p is percent. So, let me get the calculator up here and show you what I did. So you can see, you can kind of save yourself a little bit of work here. So let's get, here it is. Let me put it over here. So this is, let's see, number 45. Okay. This is, yeah, exercise 45. So let's get the calculator back. Now, I put the function in, 255p divided by 100 minus p, that has to be in parentheses. But it's a couple, I could graph it. There's a lot of different ways you can get this information out of here. Oh, in the previous example, let me show you what they wanted you to find here. They wanted you to find the difference. Let's talk about this. Okay. They wanted you to find the difference between 85% and 90%. So how are you going to, what's the easy way to do this? What's the easiest way to find this difference? Just wanted to show you something on the calculator. So let me go back to this. Example 5. And so here I put the function in just like I did with problem 45. Okay. Now, what I did was I got out of here and I went to vars, yvars, and then function, and now I got y1 on my screen. Now I put in 90, so this will give me, y1 for $90,000, okay, 720. So, and I can do y1 for 85%, okay, 453, and so I could do minus, no, I don't want to do that. Here, let's just do it like this. I'll do vars, yvars, y1 minus that's probably the fastest way to do it. Okay, so you can actually use these. You can use the function and put in an x value. So this is effectively f of 90 minus f of 85, and I get the difference between the two costs. So it costs $266,000, or let's call it $267,000, to increase from 85 to 90%. Okay, so that's a lot. So now going back to problem 45 here, I pretty much did the same thing. They wanted to know 10%, 40%, and 75, and I just used the y1 function, and I just, if you do this, let's go back. And so here you can see you can just do second and enter and just put stuff in again, change the data. I typed over it. So anyway, so that's something to try in terms of making it, making it a little bit easier on yourself. Okay, now that's A. In B, they asked you to make a graph. So here's my window. Obviously, it's 0 to 100. Scale's 10. Now, because you're dealing with an asymptote, you got to make the max. You can't make it infinity, but I made it pretty big. I made it 5,000. So, and why do you have to do that? Because 100 is an asymptote. As p approaches 100, the function, the cost of p is going to approach infinity. So you need somewhat of a big max. But if the max gets too big, then your graph, most of your graph is just going to be completely flat. You're not going to be able to see any of it. So, all right. Now start doing the homework, and if you have any questions, let me know.